Welcome to our webinar, Elevating Embedded Systems Development with C++ Useful Features. I'm Rafael Taubinger, Product Marketing Manager at IR, and I'm happy to introduce Anders Lundgren, Product Manager for ARM Solutions at IR, who will guide us through how C++ can enhance embedded systems development. In this session, Anders will share real-world examples and practical insights on using modern C++ features to boost productivity, code quality, and resource efficiency in embedded projects. Let's get started. Anders, the stage is all yours.
Thank you, Rafael. The agenda for today it will be an overview, and then we will dive into some useful C++ 17 features, and at the end we will have a summary. Let's start with an overview. In 1985, the inventor of C++, Björn Strostrup, published his book, The C++ Programming Language. However, it took some years before the language catched on and kind of made it to a bigger public. It was standardized in 1998, and that's the C++ 98 standard. And this one provided a stable foundation for software development, and it also ensured compatibility. It also brought object-oriented programming to resource-constrained embedded systems, and there was a variant called Embedded C++ that got supported by quite many of the embedded compilers. Then later on in the early 2010-ish, we had the standard C++ 11 and C++ 14. And this kind of started the era of the modern C++, enhancing productivity and performance. C++ 11 introduced autotyping, smart pointers, lambda expressions, leading to more efficient and cleaner code. Then we had C++ 14 that made further improvements for better code clarity and performance. What we will talk about today is C++ 17, and this release enhanced efficiency and made it easier to use for embedded developers. It brought features like inline variables, structured bindings for more clarity, quality, and efficient resource use. We will cover more C++ 17 in detail. We also have C++ 20 and other standards coming up. There will be a few words on that later in the presentation. C++ 17, as the name implies, was standardized in December 2017. It is known as ISO IEC 14882:2017. Some of the goals of C++ 17 was improved performance, introducing constructs that kind of would more enable the compiler to optimize, giving better code and both code size and execution times. Reducing memory usage, introducing features that would make it easy to do better memory management, to make application with smaller footprints. There is also a more intuitive syntax with new syntax and features to adding language constructs that are more user-friendly to make it easy to read and write and maintain. So why should you use C++ 17 for embedded systems? Well, it's tackling embedded constraints. It's trying to keep down the number of memory object copies And it also tries to evaluate as much as possible, enabling and providing constructs that can be evaluated at compile time instead of runtime. That leads also to boosting performance and safety. The more you can do at compile time, the better is it for both the executable size and the execution speed. It gives enhanced type safety with some new interesting constructs. It improves maintainability and clarity with syntax simplification, with kind of increased clarity, such as structured bindings. It also has an expanded standard library with facilities for expressive and concise coding. So now let's take a look at a number of C++ 17 features. I have picked 11 useful C++ 17 features that I would like to share with you now. The first feature is const if. A normal if is evaluated at runtime, and of course the compiler sometimes can optimize it to be removed even at compile time, but normally it will be evaluated at runtime. Const if on the other side is evaluated at compile time, and if it can't be evaluated at compile time, you will get an error from the compiler. This kind of is a bit similar to preprocessor operation, but this will be enhanced with type safety and integrates with C++ type system, so it will be more safe. If we look at the example here, we have a template class, and then we have an if statement, the const if, and it checks if the value passed to this function length, if it's an integer type or not. And if it's an integer type, it just returns the value. And if it's some other type, it assumes that it has a length method, and then it returns the length instead. So that means if we look at this example where we have an integer initialized to 10 and we have a string initialized to ABC, we can then use this template class function and say length ival, which is the integer, and we can also print out the length for sval, which is the strings. And looking at the output of this, if it's an integer, you get 10, and that has the value 10, you get the length 10, which is maybe not that obvious or a clever coding, but it's just an example. And in the string case, you actually get the string length, which is 3 here. So this shows how this is evaluated and completely at compile time. And this can be very useful. We also introduced the notation of how costly this feature is. And costly means in terms of performance, code size, and execution speed. And this one, since it's evaluated at compile time, is considered free. The second feature we will cover is called structured bindings, and it decomposes tuples, pairs, and structs into named variables. And this effectively becomes aliases to the object member variables, and it's actually making the code a lot more readable. And I would consider this a very useful feature. Looking at the example, we have the first statement here is returning 3 elements from a function, and instead of having this indexed in some way, you can directly say that the first one is temperature, the second one humidity, and then you have pressure, and then you can use those in code below. Looking at another example, we have a map container that we call map people age here, and we have the names, and then we have the ages. And in C++14, to get access to the elements in the map container, you would have to say first and then second. And this is not very clear to the maintainer of the code. I mean, the writer of the code probably knows very well what's meaning of the first and second element, but the ones looking at it later, it may be a bit more difficult. And looking at the structured bindings functionality available in C++17, instead you can just name them and say this is name and this is age, and then you just use them name and age instead of these first and second. And looking at the typical notation for defining a color array, a pixel, we have 3 elements, red, green, and blue. So it's very natural to say that, okay, I assign the names red, green, and blue to this and subsequent manipulations of the object. This is done entirely at compile time, so it's free. Feature number 3 is the fold expression. This expression provides a way to apply a binary operator to a sequence of values in invariant templates. This is same as the var args functionality in C, and it will greatly simplify code that operates on a variadic template argument. This could be done before C++17, but then you required a recursive template instantiation, which is kind of a bit kludgy and not that readable. So this variant with fold expression makes it a lot more readable. This could be used, for example, for CRC check computation. And the operation is, of course, fully expanded at compile time. Looking at the example here, we have a template with this fold expression specification, and it will be expanded. The number of arguments passed to this sum template will be expanded by the fold expression. And when I use it here, I say sum and then any number of arguments. In this case, it's 3 sensor readings that I want to sum. So the code here will automatically make a sum of all these 3 sensor readings. The cost of this is free since it's done entirely at compile time. std : optionals is a very useful feature. It's a formal way of handling optional values. std : optionals handles values that may not be present. I mean, it could be default values, non-initialized values, and it avoids error-prone kludgy tricks like you all probably have done. You need to flag that something is not valid or default. So you revert to selecting things that you believe will never happen in the real world, like none, not a number, or -1, or some other flag value. A real-world example of where this could have been useful is when the Ariane 501 rocket was launched from French Guiana in Kourou. Then there was 2 sensors. One sensor gave error flag values, and then the main computer saw that and it switched over to the other sensor, a redundant sensor, and that one was also sending error values because both were out of range. But instead of detecting that they were out of range in this case, the main computer decided that, okay, it must be real data. So it started acting on the real data, on the sensor values as real data, and that ended up with a disaster where the rocket self-destroyed because of this interpretation. And looking at an example here, we have a temperature reading, and if the A to D converter is ready, yes, all is fine, we have a value. But if the A to D converter is not ready, we return an empty value here, or we could as well use the std : null opt if we prefer to make it even more clear. And then in the main function, we read the temperature from this function we just have here up here, get temperature sensor reading. And then we can check on the temperature, and this check now checks if this value is set or not. It does not check on the specific temperature, it checks if we have a temperature or not. And if we have that, we can proceed processing the temperature reading. This is not free because it generates code. It's a bit costly. I did an experiment with defining a temperature as outlined in this function. And then the internal representation is that it creates the float as expected, but it also creates a flag value and then some padding. This is not that expensive, of course, but there is also some code overhead. And in this example to the right, the code increases about 300 bytes, which may or not be an issue depending on your application. We will now take a look at a construct called std : variant. It's a bit of a kitchen sink container where you can store anything, but only one item at a time, but it can be of various different types. It's akin to a type-safe union. It implements a structured way to control a union. And by knowing what type is in there, it can call in constructors and destructors, and in that way be a more controlled and nicely behaved member of the C++ class structure. Since it knows what type it is, you can query by asking query methods what type is active. Even though it's a bit like a union, I would say in the embedded space, this is probably not that very much useful feature, because when you use unions in the embedded space, you usually look at low-level behavior where you want to actually map bits and pieces between different types, and that can't be done with the std : variant. This is more like a container that can hold any one type at one time. I have labeled this one as costly because it will generate a lot of code around it. So it's in that sense also not the very best construct to use in embedded applications. Feature number 6, inline variables. Inline variables is different from inline functions. They use the same keyword, but the behavior is very different. Inline variables means that you can define a variable in multiple places without causing multiple definition errors in the linker. Normally, when you write C++ code and C code, you use the extern declaration in a header file, and then you define the variable in the C file. So you have to specify it in two different places. With inline variables, you can reduce this to only do it in one place. And you can place the inline int max sensor value as done in this example in the header file, and then you can include it from all the C files. And the linker will then collate all variables into a single definition using the weak symbol mechanism available in all modern linkers. So this is a very convenient function. It's free because it doesn't generate any extra code or variable space. Also note that all declaration of this variable, you must use the same type, of course, but since this is the idea is that you do it in a header file, this will be taken care of automatically unless you make something really wrong. C++ 17 introduces some new attributes that serves as hints to the compiler, and that means the compiler can perform steps to optimize better, or it can suppress unnecessary warnings when the programmer kind of gives a hint that this is my intended behavior. The first one is called no discard, and that will warn if a value is discarded. For example, if there is a return value that is unused. Also note that the C++ standard specifies here that the compiler is encouraged to issue a warning. There is no guarantee that this will be done, but at least the IR compiler will do this. The second attribute is called maybe unused, meaning that a value may be unused, and that's okay. Then we have an attribute that is used in switch cases that is called fall through, that tells the compiler that the switch case will not have a break and fall through to the next case statement. Looking at the examples, we have a function called compute value that we want to tell the compiler that we may skip the return value, so we specify no discard. And then in this sloppy function, we just write compute value, so we don't use the return value, and that's fine since we have declared it no discard. In this function, we say maybe unused for the result, this integer, meaning that we call the function compute value and we actually assign it to a result value here, but it may be unused and the compiler will not warn in this case since we have this attribute specified. And in the switch case, we say in this case statement we intend to drop down and proceed down to case 2, and so there is no break statement here, and instead we write fall through to make our intentions clear. This is a free feature. It's just telling the compiler our intentions. std::: shared mutex allows multiple readers to access a resource concurrently while still ensuring exclusive access for writers. And this could be looking like a tempting mechanism to use in embedded to make sure that you can lock resources and synchronize and deal with interrupts. But this is really something belonging to the desktop world where you have threads and operating system support. So going back to embedded, can it be used in an interrupt? No, not really. If you use this in an embedded system, then you will block, but you will also lock forever. since when you're in an interrupt, the main thread will be dead and the whole system will freeze, but that is not what you want. And also the interrupt handler code should be really small and really quick. So the best style to use in embedded is the old proven disable interrupt, enable interrupt mechanisms. The shared mutex mechanism could possibly be used in a real-time operating system environments, but in that case it will probably make more sense to use the more optimized mutex capabilities provided by the real-time operating system. Looking at the cost here, even if I discourage you from use it will be costly. It's a lot of code involved generated when you use this. So yeah, skip it. This is a nice one. You can use double colon to define nested namespaces. And this greatly simplifies defining nested namespaces, since the traditional syntax is quite verbose and a bit difficult to read. If we look at the C++ 11 and 14 style of declaring namespaces, you nest them by using left and right curly braces. So if you want to do a namespace that is DSP filters, FIR, and coefficients, a class, then you have to write it like this kind of indented hierarchical, a bit clumsy way, whereas in C++ 17 you just write DSP : filters : FIR, and then you can define your coefficient class within this namespace. So a very convenient way of defining namespaces. It's of course free, since this is a compile time feature. C++ 17 allows variable declarations in if and switch statements. This allows variables to be initialized with limited scope. The scope will be limited to the if-else blocks, and this in turn allows you to reuse variable names to make them defined with other meanings further down in the function. Looking at the example here, in C++ 11, you define the temperature variable on the separate line as usual, and then you kind of check on the temperature. What happens here is that the temperature variable stays in scope until the function returns somewhere down. In C++ 17, you can declare and define the variable inside the if statement like this, and then you have a colon, and then you have the condition here, which is temperature in this case. And in this scenario, this temperature variable goes out of scope after this end curly bracket. So this is a convenient way of writing more condensed and also kind of code that gets localized so that variables don't spill over outside the intended usage within blocks. The cost of this is free, since it's a compile time feature. The last feature I will share with you is a new string type called string_view. It can be used in a lot of places where you would normally use string. And it's an optimized string variant. It avoids the memory allocation and the copying of strings. It becomes a read-only copy, meaning that you can pass the reference information around without making the traditional copy operations. So there are no memory allocations done when using string view. You have a similar set of string operations, including find and substrings, etc. You can initialize a string view with a standard string or a char star or another string view. In the example to the right here, we have a function that takes a string view argument and then it prints that to standard out. We have a main function that calls our string printing function with hello world. We declare a string view and then we pass the string view argument to the print string function we have made. And compared to if this example had been using string, we saved 2 copy operations and some memory allocations. And actually there is no copy operation involved at all in this case. It's only references that gets pointers that gets passed around. It's actually sort of a free operation compared to string, but of course all string operations tend to be costly. So in that sense it's costly, but it's cheaper than a string. That's the important message. We now have reached the end and it's time to summarize a little bit. As you have seen, C++ 17 comes with a lot of nice features that will elevate embedded systems developments, both in performance terms and make your code more safe and also make it easier to maintain. You will get modern C++ features like structured bindings, fold expressions, and new attributes, for example. And by embracing these modern features, it will enable embedded systems developers to tackle challenges more effectively, leading to a more reliable and efficient embedded solutions. But wait, there is more to come. We have C++ 20 coming up with a lot of interesting features as well. For example, the 3-way comparison operator, that is also called the spaceship operator, where you can compare 2 expressions and then depending on if it's less, greater or equal, you get 0 or minus or plus as the result. So you make a complete comparison operation in one go. Plus a lot of other nice features. Then further on the horizon, we have C++ 23 as well with its own set of new extensions. That's all for this session. I hope you found it interesting. And thank you very much. And if you need more information, please visit ir.com.